Thank you for the introduction. Thank you all for coming. It's a pleasure, as always, to talk about black holes and to have an audience who's willing to listen to me talk about black holes. I understand some of you came from Toronto, so I hope you have fun. And today we're going to ask the question, and hopefully answer the question, of whether anything can ever escape from a black hole. Now, in order to ask a question like this, we need to first ask a slightly different question. What is a black hole? If we're going to ask whether something comes out of it, we better know what it is. So, what is a black hole? Well, maybe you've seen black holes in the literature, in newspapers, in science fiction, in documentaries. How many of you have heard the phrase black hole at some point before this talk? Thank you. Maybe you've seen illustrations that look something like this, and you've heard the phrase space-time is curved, and because of that curvature, all kinds of interesting and funny things happen. But most likely, the phrase that you've heard associated with black holes is a region from which nothing, not even light, can escape. That sound about right? Lots of people are nodding. I'm not hearing much, but that's okay. Now, the idea here is that light travels faster than just about anything else. It's so much faster, and not even light can travel fast enough to escape the gravitational pull of a black hole. All right, so now we understand what black holes are. Let's go back to the question that is the subject of this lecture. Can anything ever escape from a black hole? Well, didn't we just say that nothing can escape from a black hole, not even light? So clearly the answer is no, right? Am I done? Sorry, those of you who came from Toronto. At least I answered the question. Is that it? Well, I do have another 45 minutes to talk, so you might guess this, maybe there's more to the story. And indeed, this conclusion is a little fast. So there's a lot more we need to get into here. Now, it turns out, interestingly, that black holes, it's not super communicating very well, that black holes have a certain property, so that if nothing ever escapes from a black hole, and again, we're going to talk about all of this in a lot more detail, but if nothing ever escapes from a black hole, then information, and we'll talk a lot about what information means, but for now, think of it as something you might write down in a book. Information can be destroyed. And we're going to explain why that happens and what do we mean by information, but to sort of give you a quick understanding of why we can't quite just say that nothing ever escapes from a black hole and that's the answer to the subject of this lecture. There's a problem here, which is that if information can be destroyed in a very basic aspect of quantum mechanics, which is the theory that describes the minutiae of our universe, the electrons, the quarks, the basic fundamental building blocks, that theory is wrong. And I have to say that quantum mechanics is a pretty good theory. It's a theory that has been tested, and it has been tested again, and again, and again, and so far, it has not been wrong. So what do we have here? We have two apparent truths. One is that nothing can escape from a black hole. We've all read it in Scientific American. And the other is that we have quantum mechanics. And quantum mechanics is also a theory that has not been wrong. So we have two apparent truths that cannot be mutually true at the same time. In other words, we have a paradox. This is known as the black hole information paradox. It's a very old problem in theoretical physics. It's a 50-year-old problem. It's kept a lot of us in the business, and it has been a tremendously insightful thing to study. And it is the primary subject of the lecture today, the black hole information paradox. And we are going to unpack it in the next 45 minutes. So we're going to start by just unpacking the phrase black hole information paradox. Well, it contains the phrase black hole. And black holes are massively gravitating objects that were predicted by Einstein's theory of general relativity. The theory that describes gravity on large scales of the cosmos, clusters of galaxies and black holes and stars. That's Einstein's theory of general relativity. We have this second phrase here, second word rather, information. And as I mentioned, we're going to get more into what we mean by information, but really we mean quantum information, which is to say that the second thing that goes into this is quantum mechanics. And of course, we have paradox. So we have gravity, on the one hand, that feeds into this black hole information paradox, and we have quantum mechanics, on the other hand, that also feeds into the black hole information paradox. We have two pillars of nature, two fundamental theories that describe our universe that are both going into this problem that we're going to study today. So the black hole information paradox is a problem that confronts the quantum nature of our universe, the fact that we have quarks and electrons and protons and all of these things, these basic tiny building blocks that interact via the theory of quantum mechanics to the best of our measurements, together with general relativity that describes everything else in the universe, more or less, that involves gravity. Well, these two theories might seem really different, but they share something in common, which is that they're both theories of the extreme. So quantum mechanics is a theory of really, really small things. So you might have seen this picture here associated with quantum mechanics. You might have other associations with quantum mechanics, subatomic particles such as electrons, quarks, quantum computers, some very, very weird movie plots. General relativity is the theory of very large things. So this is a kind of picture you might associate with general relativity. We're talking about grand scales in the cosmos. We're talking about stars and galaxies, other associations you might have with this, black holes, wormholes. Another thing it shares in common with quantum mechanics is really weird movie plots. And so we have these two theories, both theories of the extreme, and I'm claiming that we have a problem between the two of them. But you might say, hang on a minute. This is the theory of really small things. And this is the theory of really large things. So there can't possibly be a problem because they just don't apply to the same things. Well, I omitted something important. The theory of quantum mechanics applies to things of small size, and the theory of general relativity applies to things of large mass. And so maybe we might worry that things that are small in size but high in mass might require us to have both quantum mechanics and general relativity. So for example, if we have some very massive object, a star, here I've shown a planet, and we take it and we just really, really compress it to really, really small sizes, like the size of an electron, the size of a proton, something quantum mechanical. Well, the law says that if you take something and you collapse it into a really small size, and it's like a star, then it forms a black hole. And now we have a situation where we have a huge amount of mass, and we put it in a really tiny space, and now we might need to worry about both gravity and quantum mechanics. Which means we have to worry about quantum gravity, a quantum theory of gravity that incorporates both. Now, quantum gravity is not something that we can see in this room. I'm not seeing any quantum gravity here. It's a theory that applies to very extreme regimes. It takes two very extreme theories, and it applies to regimes that are even more extreme than either one. Where might we see quantum gravity? Well, the Big Bang is an example where we might expect that quantum gravity becomes important. We would not be able to describe the Big Bang without understanding quantum gravity. The Big Bang is the beginning of the universe, where you might imagine that we've taken everything there is in the universe and condensed it into something incredibly, incredibly tiny. And then we have a huge amount of matter, a huge amount of mass, concentrated into a tiny quantum mechanical space. Maybe something like 10 to the minus 34 meters by 10 to the minus 34 meters by 10 to the minus 34 meters. That's really, really, really small. So we might want quantum gravity to describe those kinds of phenomena. Another example is a particle accelerator that's a whole lot bigger than what we currently have the capability to build. And The third example, so this is something, particle accelerators, of course, we have at CERN, but not of this size. This is comically obvious. And the third example is the interior of a black hole. Now, looking at these three, you might say, I'm not seeing anything I can put in a lab and directly observe quantum gravity. And that's part of the thing that makes quantum gravity very difficult. We would like to be able to understand all of these, but empirical data is very hard to come by. Nevertheless, we don't understand quantum gravity well yet, but we are driven. And we are driven because there's a lot that we can explain once we have a good quantum theory of gravity. We'd be able to explain how the universe started. Anyone wants to know the answer to that? We would be able to explain or answer the question of, does before the Big Bang make sense? Is there such a thing as time? Can we make sense of it? And of particular interest to us today, what happens when you jump into a black hole? And so you might say, okay, well, you're a physicist. We would like answers to these questions, please. What's the problem? Go do some work, figure out quantum gravity, and tell us the answer. Fair? But quantum gravity is really hard, like really hard. And we don't have empirical data to help guide us in our quest for understanding quantum gravity. So what's the strategy? How do we go about trying to understand, trying to solve quantum gravity, trying to answer the question of whether anything ever comes out of a black hole? And one way to do it, one thing that we like to do, is thought experiments. Gedanken experiments, if you like. So there's this kind of this image sometimes of theoretical physicists as sort of, we sit back in our offices and we kind of stare off into the distance, and then eventually we say, Eureka. It's a bit of an idealization. But it's true that we spend a lot of time thinking and coming up with scenarios. Thought experiments are experiments we can't do. We can't jump into I don't know how to jump into a black hole and do the measurements that I need to do. But I can imagine what it looks like. I can write the equations. I can try to figure it out. So we're going to do a number of thought experiments in this lecture, and that's going to help us understand whether things come out, information comes out of a black hole. So we can ask, okay, we have a black hole. What would general relativity tell us? What would quantum mechanics tell us? And if we have a contradiction between the two, then we've got ourselves a paradox. And you might say, that sounds terrible. Why would you ever want that? And the answer is, paradoxes are great. We love paradoxes. Why do we love paradoxes? Because they tell us when we're thinking about something in the wrong way. Here we have two pillars of nature, quantum mechanics and general relativity. And they both appear to be true, but something must give. And in understanding which one of them is false, or maybe they're both false, in understanding that, we will have learned something fundamental about nature, about quantum gravity. That is why we love paradoxes, because they're telling us there's something we don't quite understand when we say that general relativity and quantum mechanics are both pillars of nature. So we have a paradox that tells us where to focus our efforts and what we need to understand. Now, usually, we like to also resolve paradoxes. This one is a thorny one. It's been around for 50 years. But the exciting thing is that in the past few years, we've made a tremendous amount of progress on this. And I will give some answers before the end of this lecture. Okay. So again, we are talking about the black hole information paradox. In case you forgot, it's a contradiction between the predictions of general relativity and the predictions of quantum mechanics due to the behavior that we'll talk about of black holes. So here we are. We've got ourselves a problem. Now, that means that we're going to have to study general relativity, and we're going to have to study quantum mechanics. Now, normally when I teach general relativity to my graduate students, it takes me about 3 months to lay down the foundation. But you seem like a very dedicated audience. Some of you made it here from Toronto. So we're going to do it in like 5 minutes. All right, general relativity. What is the basic idea? Basic idea is that mass curves space and time. And you probably have seen pictures like this before, and people will say, that's the fabric of space-time, and now you understand everything. And I like to use analogies because they're very helpful. So what does it mean to say that mass curves space and time? Let's think of a situation where maybe you're sitting in a motorboat, and you're at the top of a waterfall. And all you want is to not fall into the waterfall. Now, if you just sit there, you'll fall into the waterfall. But maybe if you turn on the motor and you try really hard to go the other direction, you'll be lucky and you'll sort of stand still. The idea behind this is the same thing. If you're sort of skirting by a black hole and you're trying really hard not to fall in, it's not enough to just sit there. You'll end up going through the waterfall with no point of no return. What you need to do is you need to try to accelerate as much as you can away from the black hole, and then maybe, if you're lucky, you'll end up sort of standing still. That's the general idea behind this idea that mass curves space and time. Just think of the waterfall. Now, a black hole curves space and time a lot in a very dramatic way. It concentrates just so much mass into such a tiny region that nothing can escape it. You could think of it again kind of like the waterfall, where once you're over it, there's kind of no motorboat that's going to get you back up the waterfall. Now, it's helpful to think of some numbers. Think of how massive is massive and how small is small. So if you take a black hole, which is 1,000 times the mass of Mount Everest, and you collapse it to the size of a single coronavirus variant, that would kind of be a black hole. That's the amount of matter that we're concentrating into a really tiny space. It's a very extreme regime. All right. Now, it's very important in everything I said in the previous slide that nothing travels faster than light. Right? I said, it curves space-time so strongly that nothing can escape, not even light can escape. We keep on talking about that. So it's important to understand what is the relationship between the black hole and this idea that nothing travels faster than light. And I like to use a schematic, this kind of light cone type schematic here, to explain how that works. So the idea here is that time is kind of moving upwards here, and you have some kind of a flashlight over here. So there's me. I'm standing with a flashlight over here. This cone of light is everywhere that light can travel to. Everywhere outside of the cone of light, light is not fast enough to get there. Light travels at a particular speed, 3 × 10⁸ meters per second. And to get here, I'd have to travel faster than that. Since time runs upwards in this diagram here, me being slower than light, I'm confined to within this light cone. All the possibilities of my future are within this cone of light over here. I mean, it sounds a little doomsday, but there's nothing wrong with traveling slower than light. We all do it. Now, to give you an idea of what's going on here, you could say, okay, maybe I have my work desk, where I'm going to sit, dreaming and saying eureka, and I would like to get to my work desk. Well, at present, at this moment, my work desk is sitting outside of the light cone. I can't travel faster than light, so I have to wait. Now, the work desk is itself traveling in time until eventually it enters my cone of light. Once it enters my cone of light, that's the place that I can reach. So I'm also traveling, and I'm able to get here to my desk at this time. So again, the main takeaway from this is that all the possibilities for me are within the cone of light. Everything outside is faster than light. All right, what does this mean for black holes? So here I've drawn a black hole, the schematic of a black hole. So this sphere here, this ball, I'm drawing time again is running up. So this is a ball here at a single moment in time. And it's undergoing gravitational collapse. So its radius is shrinking as a function of time. And again, time, every moment here, every horizontal slice is a moment in time. And so the black hole is shrinking in radius. It's collapsing under the force of its own gravitational field. And then eventually an event horizon forms. OK, so we have this event horizon over here. What does it mean? Why is it that nothing can escape? Let's take a look at the cones of light in this universe containing this black hole. So if I'm sitting here very, very far away from the black hole, and I'm holding my flashlight, this is the cone of light. So these are my possible futures. As you get closer and closer to the black hole, you'll notice that the light cones begin to tilt. This is a way of saying that these light rays are having a sort of a harder and harder time staying away from the black hole. More and more of my trajectories are pointing towards the black hole. And something interesting happens when you cross the event horizon. This is the light cone that first crosses the event horizon. There is no trajectory for me that can ever exit the black hole. In fact, the light cone itself, the boundary of this cone of light, just barely stays on the edge of the black hole. And anything slower than that is going to go right in. And this continues for all of the other cones inside of the black hole. So this is what's going on. This is why we say nothing that does not travel faster than light can escape from the black hole, and nothing can travel faster than light. Because this is what light is doing. The event horizon, you can just barely hug it if you're a light ray. Anything slower, it's going to go straight in. All right. That's it for general relativity. We're done, 5 minutes, that's it, just like that. Now, quantum mechanics is going to take us a little bit longer. And you might ask why? Because it's more nuanced, shall we say. The basic idea, there are many basic ideas behind quantum mechanics, but I'm going to focus on one. And I'm going to focus on one aspect of quantum mechanics as well. But the basic idea is that outcomes of experiments are probabilistic. And rather than going into the full theory of quantum mechanics, I'm going to allow the founders of quantum mechanics to justify for me why I'm not doing it. Maybe you walked outside, and outside the theater, you saw all these little posters dedicated to the founders of various fields in physics, and there were a couple dedicated to founders of quantum mechanics. And I'm going to quote those here. So the first one is Niels Bohr, who said that anyone who is not shocked by quantum theory has not understood it. And the second one is by Paul Dirac, who said, I think it is safe to say that no one understands it. And I spent a while thinking, does that mean that Paul Dirac saw this and said, oh, I'm not shocked, so maybe I don't get it? Or maybe he didn't quite agree with Niels Bohr. I don't know. Either way, I'm going to try not to shock you too much. So we're not going to try to understand quantum mechanics in full. But we are going to try to understand a very specific aspect of it, which is very important for the black hole information paradox. And we're going to start by doing a Gedanken experiment. So we're going to start with a classical coin. You can ignore the word classical for now, it just means non-quantum. We haven't talked about what a quantum coin is, so just a coin. Very simple situation. We have a coin, we have a treasure chest, and the coin is in the treasure chest. Now, we haven't looked at the coin, we don't know how the coin got there, we don't know who put it there. So there's a 50% chance that this coin is heads up, and a 50% chance that the coin is tails up. Okay? Now, we can open a treasure chest, and we can look at the coin. We're going to call that doing a measurement of the system. All right? We open it, we look at the coin, and we say, it's heads up. Then we say the state of the coin is heads. We did a measurement, we found that it's heads. That's the state of the coin. Now, if we had 1,000 identical treasure chests that someone prepared in the exact same way, meaning they placed the coin in each one of these in the exact same way, then we know that if we opened every single one of them, if we did a measurement on every single one of those, we would find heads for every single one. That's the classical coin. Now, maybe many of you are maybe thinking, okay, tell me something I don't know. Challenge accepted. Now we're going to talk about a quantum coin. Suppose you have a quantum coin in a chest. Now we know that quantum mechanics tells us that the outcomes of measurements are probabilistic. That's what we started out with in quantum mechanics before we got derailed by various quotes of the founders. So we have 1,000 coins in a chest, but we say the outcomes of measurements, those outcomes are probabilistic. So we make measurements on 1,000 identical coins, and 500 of them will be heads, and 500 of them will be tails, even though they were prepared in the exact same way. We did measurements on those systems, and we found many very, very different outcomes, 2 different outcomes. What do we say about the state of the coin? Well, if you had 1,000 coins and 500 of them were heads and 500 of them were tails, then we say, well, the coin is 50% heads and it's 50% tails. The coin is heads and tails at the same time. Now, it is common practice to use a cat to do this. And we talk about whether the cat is alive or dead. And I prefer not to harm, I'm allergic to cats, but I prefer not to harm animals in doing my science. So we're going to talk about coins. But if you've seen the cat alive or dead scenario, this is the same thing in a less harmful disguise. Okay, so this is the state of our coin. It's 50% heads, 50% tails, which means that a quantum coin is heads and tails at the same time. And we make different measurements on it, and we find a probabilistic distribution. Now, we can also have a loaded quantum coin. Right? It doesn't have to be 50-50. Maybe we have a state of the coin which is 80% heads and 20% tails. What does this mean? Well, it means if we have 1,000 coins and we do a bunch of measurements, meaning we open each one of those boxes, and then we're going to find that 800 of those coins are going to be heads, and 200 of those coins are going to be tails. That's what a loaded coin looks like. So the basic upshot is that a single measurement doesn't actually tell us very much. Right? If you say, okay, there's some coin, it's some quantum coin, it's in some state, some percentage heads and some percentage tails, and I open one box, and I find that it's heads. What does it tell me? I don't know. Maybe this is the one box out of the 200 that are tails, or that are heads, and 800 of them are tails. Maybe it's the one box that out of 1,000, the one heads, and all 999 are tails. It doesn't tell me very much about the actual state of the coin. It doesn't tell me if it's 99.9% heads and 0.1% tails, or 60% heads and 40% tails. All it tells me is that it's not 0% heads. However, if I make measurements about many identical copies, 1,000 copies, and I find 800 heads and 200 tails, that tells me a lot. It tells me the state is, more or less 80% heads and 20% tails. So you can basically get the information that you want about the quantum coin as long as you can make enough measurements, as long as you have enough copies and you can make enough measurements, open enough of the treasure chests. Okay. Now, one quantum coin is easy. We're experts on that at this point. It's all 100% clear. Let's talk about 2 quantum coins. Make the story a little more interesting. If we have 2 quantum coins, we have 4 possibilities. If we open a box, 2 coins inside, they could both be heads. You could have coin 1 be heads and coin 2 be tails. You could have coin 2 be tails and coin 1 be heads. And then you can have both of them be tails. All of these are the 4 possibilities when you have 2 quantum coins in a box. Okay. Now, this actually leads us to something that was called spooky action at a distance. So let's modify our thought experiment a little bit. We're going to say, we're going to have coin 1 over here, and we will have coin 2 sitting here in 2 separate treasure chests. We have 2 quantum coins, and they're sitting in 2 separate treasure chests. And I'm just going to open one of the treasure chests. I'm not going to open the other. We're going to take some this is going to be a loaded pair of quantum coins. So this is going to be the state of the quantum coins. It's not 25% on each one of the 4 possibilities. It's going to be 50% on the first possibility we had, and 50% on the second possibility that we had. That's our loaded pair of quantum coins. And again, it's 2 quantum coins, one sitting here and one sitting over there. Now, if I'm going to open the treasure chest of the first coin, and I'm going to find that it's heads, then that immediately means that I'm not in this situation over here. Instead, I'm in this one. So by opening the treasure chest over here, measuring it, finding that this is heads, that means that that one over there is also heads, even though it's over there, and I haven't done anything to it yet. Just by making the measurement and finding that I'm here. This type of relation in a quantum state is something we call entanglement. It's these two coins, we say that they are entangled with one another. And entanglement is a key property that we're going to leverage to understand the black hole information paradox. So let's talk a bit more about entanglement. So here's this loaded pair of quantum coins. And we're going to talk about the entanglement between them, the fact that I can do a measurement on one and somehow impact the other, apparently. So entanglement is a relation between these two coins. You could say, OK, but what does that mean? It means that if you just measure coin 1, or if you just measure coin 2, without knowing that they are entangled, then you miss out on crucial information about the two-coin system. If I just measure coin 1, I didn't know it was entangled with coin 2, I won't know that coin 2 is now heads. I won't know that. So you're missing information, and this is why we're talking about entanglement, because it's related to quantum information. So let's talk about this a little bit in more detail. So we have a pair of quantum coins. In principle, they're in some quantum state. We don't know what it is, which means we don't know what the values are, what are the percentages, what's the probability of each one of these possibilities. And I claim that when two particles are entangled, then if we make measurements about just one of them, then we're going to somehow miss some information about the system. So let's see this a little bit more in action. So we have two entangled coins, as we discussed. In this state, if we measure coin 1, we get heads. Then we know coin 2 is heads. It's now heads. Now let's take another pair of entangled coins. It's this one. So it's a different pair of a loaded quantum coin. It's entangled in a different way. You'll notice this one is heads, tails, plus tails, heads. I open the box, and I do a measurement on coin 1, and I find heads. And that means that coin 2 is now definitely tails. But if I were in this state, it would mean coin 2 is now definitely heads. And if I didn't know the way that these two coins are entangled, I wouldn't know whether coin 2 is now heads or whether coin 2 is now tails. I'd be completely ignorant, missing crucial information about the state of the two quantum coins. So we don't know the state of the quantum coins. Measuring coin 1 puts coin 2 in this definite state, but we don't know what it is. And this is, again, this point that when two particles are entangled, if you have access to just one of the two particles, then you're missing information. OK. Oh, I'm sorry, I'm going in the wrong direction. That's why it's going back up. OK, great. All right. So now suppose we have the state of the, I promise we're almost done with coins, really. We have 1,000 identical chests with two pairs of coins. They're all prepared in the same state. We don't know what that state is. We look at coin 1 in each one of these, and we find heads every single time. What can we conclude? Well, we can conclude that we're not here, and we're not here, right? Because we found heads every single time, so this is very, there are no tails. But we know absolutely nothing about whether we're here or here. Totally probable we could be in the head state for the coin 2 or in the tail state for coin 2. We have no knowledge of the matter. So we're missing essentially all the information about the state of coin 2. Even though we made measurements on coin 1. It's completely determined by our measurement on coin 1, and we know nothing about it. So again, when two particles are entangled, having access to just one of the particles, it misses information. Now, I promised enough with the coins, so let's go back to black holes. How does this all relate to black holes? Well, I'm just going to throw a fact out there. It's a bit of a caricature of what happens, and in some senses, you could say it's the most outrageous part of this talk. And I'm just going to tell you that it's true. That pairs of entangled particles, which you can think of as entangled coins, are sort of popping in and out of existence all the time in our universe, right here, right now, all the time. That's because you can't see it, doesn't mean it's not happening. And this continues to happen across the event horizon of a black hole. Why shouldn't it? Right? You can cross the event horizon of a black hole. Why shouldn't entangled pairs of particles just pop into existence across the event horizon of a black hole? So here's our black hole curving space and time, just like the waterfall. We have two coins, two particles, if you like. that are entangled, that popped into existence across this event horizon of the black hole. One of them went into the black hole. The other one, the one that popped up outside of the event horizon, stays outside of the black hole. But they're still entangled. This carries energy away. This is what is known as Hawking radiation. This particle had some energy, and it is carrying it away from the black hole. Carrying it away from the black hole means we're sort of taking energy away from the black hole. And so as a result of that, the black hole loses energy. And you can say loses mass, if you like, and it shrinks. And it keeps on shrinking until eventually it evaporates altogether. So through this process of particles popping in and out of existence across the event horizon, carrying energy away, a black hole can shrink and eventually disappear altogether. Now, of course, if you keep on throwing things into the black hole faster than this process is happening, then you won't see the black hole disappear. But if you just kind of leave it alone and don't let any accreting matter fall in, just wait, then the black hole will evaporate altogether. Okay, well, let's take a look at the coin that flew away now. Right? Remember, before we started talking about this fascinating process, we talked about entangled pairs. And there's a coin that went into the black hole that disappeared. And there's a coin that's left. Let's take a look at the coin that's left. We're going to look at it, we're going to measure it, and we're going to find heads. Okay, we found heads. What does that mean about the coin that ended up inside the black hole? Well, remember this story of entanglement. When two particles are entangled, having access to just one misses information about the system. We only have access to one, just the coin outside. But maybe we want to learn about coin two. Why don't we just learn something about coin two? Well, you could say, okay, if you really want to, you're willing to do that, you can just jump into the black hole. It's a bit of a sacrifice to make to learn something about the state of coin two. I might not advise it, but you could do it. Well, you could do it before the black hole has evaporated. But you can't jump into a black hole that's gone. Once the black hole has evaporated fully and is completely gone, the coin that went into it has disappeared. It's gone from the universe. There's nothing you can do. You can't jump into a black hole that doesn't exist to recover the state of coin two. There's no observer in the universe who can measure coin two. Coin two went into a black hole. The black hole disappeared. Okay. Well, that means the disappeared of coin two. Quantum entanglement tells you, this is a result of Stephen Hawking's, quantum entanglement tells you that if you're only measuring coin one, you're missing information. But it's not possible to measure coin two because it's gone. The fact that black holes evaporate leads to a net loss of information in the universe. The black hole took coin two, and it made it go poof. And now, what are we going to do? We've lost information. We have coin one, and coin two disappeared, but coin one does not contain complete information. Information was lost. This was a great insight of Stephen Hawking's that generated all this activity, and this was the discovery of the black hole information paradox. So here we are, the black hole information paradox. So black holes can evaporate. This is the key insight, because if they couldn't, then you could always jump into the black hole, catch coin two, make their measurement. It might not be an easy thing to do, it might not be a safe thing to do, but it certainly is a thing you could do. And so you couldn't say that, information was actually lost. You could just say information has become unpleasant to recover. So black holes do evaporate, though. They evaporate, and we are now left with the question of, what do we do with the remaining thing that's left? So general relativity says, due to evaporation, information about coin two is irrevocably lost. Why? Because nothing can escape from a black hole. It went into the black hole, and nothing can escape from a black hole. And it was entangled with coin one. And we know that if you only have coin one, you're missing information. And so the fact that the coin went into the black hole and nothing can escape from it meant that information has been lost. And then quantum mechanics comes in and says, I'm sorry, but there's no process in the universe that can lose information. And here we are with two things that appear to be true, and we now understand a little bit better why is it that they're giving us opposite answers. General relativity, information is lost. Quantum mechanics, information cannot be lost. And now we have to understand what actually happens, and how do we square with the fact that at least one of these, maybe if not both, is actually wrong. Every experiment that we've done appears to suggest that general relativity is a good theory of gravity. And every experiment we've done tells us that quantum mechanics is a good theory of the small quantum world. But of course, we haven't done the experiment of jumping into a black hole and asking what really happens. So, remember, we love paradoxes. We shouldn't be frustrated. We got a paradox. This is exciting. How do we modify our theories to describe nature properly? That's what we need to understand. But where is our mistake? So in this case, our mistake is that we need to understand quantum gravity. We need to work harder. We need to understand the theory that describes these very extreme regimes. All right, black hole information paradox. That's what the problem is. Now, of course, I told you that we've made a lot of progress in the past few years. So where are we at now? It's exciting to talk about the black hole information paradox now because we understand it so much better, and we have some answers. So where are we now? What's missing? What do we need in order to resolve the black hole information paradox? You could say, well, you guys could, do your jobs and find a complete quantum theory of gravity, please. Thank you. Yes, we could. We're trying. Cut us some slack. This is hard, so hopefully we don't have to do this in order to solve the information paradox. We could try to ask, maybe gravity does something unusual to entanglement. Maybe gravity interacts with entanglement in some way. Maybe it impacts entanglement in some way that restores this entanglement to coin one, some way that somehow restores the information. It's a little dicey, because if it restores the information came out of the black hole, so something traveled out of the black hole. But maybe we need to try to understand this a little bit better. Another possibility is we could say, maybe we don't quite understand the process of black hole evaporation very well. Maybe there are some things you forgot here and there. Maybe there's some small correction here and there that eventually adds up and makes this look very, very different. Now, there's actually some theorems, results that show that this is not going to help us. Even if we understood the evaporation process a bit better, it's not going to change the big picture of the paradox that we have. So that leaves us with this, which we're trying, but we haven't really succeeded, or this. Maybe we should ask what happens to entanglement, which is maybe different in gravity than in just ordinary quantum mechanics. So, in May 2019, 2 papers came out on the same day, and it wasn't a coincidence that they came out on the same day. It was the coordinated co-discovery, these 2 papers here, that probed exactly this question of what is the behavior of entanglement and gravity in an evaporating black hole using modern tools that were discovered in the 5 to 6 years before that, and gave us a new handle on understanding and tracking entanglement in a gravitating phenomenon through time. And you can ask, what did these see? What was exciting and new about these papers? Well, these papers found that gravity does contribute to entanglement, maybe in ways that we hadn't anticipated. Certainly in ways that I, as a co-author of one of these 2 papers, had not initially anticipated. And it turns out that the way in which gravity impacts entanglement in an evaporating black hole is just exactly enough to offset the loss of information due to evaporation. And I want to emphasize how sort of miraculous that is, that it comes in exactly in the right way, with the right sign, at the right amount, at the right time. and works out to exactly offset this so that all of a sudden it doesn't look like we have information loss anymore. And I remember when we were working on these papers, I'm on this one, we're working on this, and I remember the moment at which I realized that I think this is it. And I was driving home, and it was pouring, and I was driving home from the office after meeting with my collaborators, Ahmed Al-Amhari, Don Merrill, and Henry Maxfield, and I was thinking, I think we got it. I think it works. And it didn't have to work. It didn't have to be exactly right, just barely right to make it happen, but it did. And that's something really deep and fundamental. And it turns out that we didn't have to totally give up on, general relativity in order to make this happen. It sort of came in, impacted entanglement in just the right way. Now, that still leaves a number of problems to try to solve. I would say it's clear the information gets out. So, does anything come out of the black hole? Yes. And there's a way in which gravity manages to get the information from the black hole to outside of the black hole. But now we're sort of back to where we started, saying, hang on, does that mean that general relativity is actually really wrong? Because according to general relativity, nothing can ever escape from a black hole. Nothing travels faster than light. So how could the information get out? So sure, okay, the information gets out. Thank you, reassuring. But nothing travels faster than light, and light can't escape from a black hole. So how does the information get out? If you're an astronaut and you jump into the black hole, you'd like to know, how will I get out? Again, I don't advise it. All right, that's confusion. Can quantum gravity somehow transport stuff faster than light? I'm whispering because I'm a little, scared to say it. You can still hear me, I'm mic'd up. But shouldn't we have already seen this? We have never observed, to our knowledge, faster than light travel. So shouldn't we have already seen information transferred being faster than light if quantum gravity does it? Why have we never seen this? If that's what happens, information gets out of black holes, that means something can travel faster than light, so how come we haven't seen that? So, towards a resolution. Now, information has been transported out of the black hole, but even though that did happen, it turns out the information has been scrambled in the process. No one ever guaranteed to the astronaut that they were going to be manifesting outside of the black hole in pristine form. Information gets scrambled and mangled in the process, and it's so scrambled and it's so mangled that it is so incredibly difficult to tell that the information that went into the black hole came out, because it's come out in this huge jumbled mess that ended up in the Hawking radiation of the black hole. Could that be why we haven't sort of seen faster than light travel? Because when information does travel faster than light, it's just incredibly messed up that it's very hard to kind of undo the process and see that information traveled faster than light. You say, okay, hang on, this is getting a little philosophical for me. What do you mean by difficult, and how difficult is difficult? What are we talking about here? All right. Well, the information comes out in some quantum state, right? We talked about that. Information is encoded in a quantum state. Information comes out in some quantum state. So here's some quantum state, and then this long chain of quantum coins, some probabilities of different heads and tails and so on. Now, if there are n coins in the box, n is some integer, then there are 2 to the n possible combinations of coins. Let's remember, when we had 1 coin, well, we have 2 possibilities. When we had 2 coins, we had 4 possibilities. If you have n coins, you have 2 to the n possible combinations of coins. All right, so that's just telling us about the quantum state. Information comes out in some quantum state. It's some scrambled quantum state. So it's some representation of these n coins, and there are 2 to the n such possible ways for them to be arranged. And only one is the right one. The way information comes out, there's only one. To unscramble everything, we need to get back to the same state that we had before. So only one state is the right state. So if you want an algorithm that figures out which combination you actually have, what's the unscrambling algorithm, it has to sort of sift through 2 to the n possibilities before it says, that one, found it. And if n is 1 or n is 2, that's not so bad, but what is n for a black hole? Is it 1 or 2? Maybe then we should sort of already have seen it. Well, for a solar mass black hole, n is about 10 to the 70. So we're talking about an algorithm that would have to find this needle in a haystack of size 2 to the 10 to the 70. I don't know about you, but I can't imagine a number that big. It is beyond my comprehension, and I deal with big numbers kind of a lot. That is how difficult it would be to find, to decode the radiation, as we call it, to figure out, to see that the information has come out. So you could say, okay, but sifting through it seems a little primitive. Maybe quantum computers, I've heard a lot about quantum computers. This is a quantum coin. Maybe a quantum computer could do better than just sort of sifting through all the options. Maybe a quantum computer, will show us that we can travel superluminally. Maybe I wouldn't have to fly home at the end of this week. We could just kind of, teleport myself. As it turns out, even a quantum computer, it can speed up the process a little bit, but it can't actually speed it up by a lot. Just a small factor. So nothing appears to travel faster than light, but to see that faster than light travel has actually happened, that requires unscrambling. The information came out in some messed up state. You have to return to the original state. And to do that, you have to do an operation that's as difficult as sifting through 2 to the 10 to the 70 combinations to find just the right one, which is incredibly hard. That's why we haven't seen any of it. Well, one possible explanation. So we started out asking, does anything escape from a black hole? And we learned general relativity, we learned quantum mechanics, we learned that there's a problem, and we learned that there's a resolution. And hopefully, we all learned that, yes, everything that falls into a black hole can escape from the black hole, and does escape from the black hole if the black hole evaporates. Everything. Otherwise, we have information loss, and we know that's not what we have. But it also escapes in an extremely mangled way. I like to call this the principle of conservation of misery. Sure, it escaped, but your life is not going to be so easy that you can just read it off. Now, it's going to take a very, very, very long time to take this very mangled thing and rearrange this mangled thing into its original form. And that is maybe that's the reason that we haven't seen this yet. So, is this the final resolution of the black hole information paradox? To be honest, I've presented you with my perspective on it. Others may take a different one. What's the basic mechanism in quantum gravity that mangles up the information in the black hole? I haven't told you that. I don't actually know what the answer is to that. Another question, what really happens to coin 1 in the black hole interior? I told you that the astronaut can sort of jump in, and information about the astronaut will come out in some mangled up form. But what happens to the astronaut? What's the experience of the astronaut as he jumps in and as the information about the astronaut eventually makes it out? What does the astronaut feel? I don't know. These are all questions that we are still answering, that we're still trying to decode, if you will, information that we are still trying to obtain. So, resolving the black hole information paradox fully, including those 3 questions that I just asked, that's a stepping stone. It's a stepping stone to understanding the fundamental building blocks of the cosmos, of the Big Bang, of black holes, of quantum gravity, which is the most fundamental description of our universe, of all of its phenomena in extreme scales. To answering the question that I would say has fascinated humanity for as long as human thought has existed. Where did it all come from? Thank you for your attention.